In this lesson, we are going to write code to delete a node from binary search tree. In most data structures, deletion is tricky. In case of binary search trees too, it's not so straightforward. So let's first see what all complications we may have while trying to delete a node from binary search tree. I have drawn a binary search tree of integers here. As we know, in a binary search tree, for each node, value of all nodes in its left subtree is lesser and value of all nodes in its right subtree is greater. For example, in this tree, if I'll pick this node with value 5, then we have 3 and 1 in its left subtree, which are lesser, and we have 7 and 9 in its right subtree, which are greater. And you can pick any other node in the tree and this property will be true, else the tree is not a BST. Now when we need to delete a node, this property must be conserved. Let's try to delete some nodes from this example tree and see if we can rearrange things and conserve this property of binary search tree or not. What if I want to delete this node with value 19? To delete a node from tree, we need to do two things. We need to remove the reference of the node from its parent, so the node is detached from the tree. Here we will cut this link. We will set right child of this node with value 17 as null. And the second thing that we need to do is reclaim the memory allocated to the node being deleted, that is, wipe off the node object from memory. This particular node with value 19 that we are trying to delete here is a leaf node. It has no children. And even if we take this guy out by simply cutting this link, that is removing its reference from its parent and then wiping it off from memory, there is no problem. Property of binary search tree that for each node, value of nodes in left should be lesser and value of nodes in right should be greater is conserved. So deleting a leaf node, a node with no children, is really easy. In this tree, these four nodes with values 1, 9, 13 and 19 are leaf nodes. To delete any of these, we just need to cut the link and wipe off the node. That is, clear it from memory. But what if we want to delete a non-leaf node? What if in this example we want to delete this node with value 15? I can't just cut this link, because if I'll cut this link, we will detach not just the node with value 15 but this complete subtree. We have two more nodes in this subtree. We could have had a lot more. We need to make sure that all other nodes except the node with value 15 that's being deleted remain in the tree. So what do we do now? This particular node that we are trying to delete here has two children or two subtrees. I'll come back to case of node with two children later because this is not so easy to crack. What I want to discuss first is the case when the node being deleted would have only one child. If the node being deleted would have only one child, like in this example, this node with value 7, this guy has only one child. This guy has a right child but does not have a left child. For such a node, what we can do is we can link its parent to this only child. So the child and everything below the child, we could have some more nodes below 9 as well, will remain attached to the tree and only the node being deleted will be detached. Now we are not losing any other node than the node with value 7. This is my tree after the deletion. Is this still a binary search tree? Yes, it is. Only the right subtree of node with value 5 has changed. Earlier we had 7 and 9 in right subtree of 5 and now we have 9, which is fine. What if we were having some more nodes below 9? Here in this tree I can have a node in left of 9 and the value in this node has to be lesser than 12, greater than 5, greater than 7 and lesser than 9. We are left with only one choice. We can only have 8 here. In right we can have something lesser than 12 and greater than 5, 7 and 9. All in all between 9 and 12. Okay, so if the original tree was this much after deletion, this is how my tree will look like. Okay, so are we good now? Is the tree in right a BST? Well, yes, it is. When we are setting this node with value 9 as right child of the node with value 5, we are basically setting this particular subtree as right subtree of the node with value 5. Now this subtree is already in right of 5, so value of all nodes in this subtree is already greater than 5. And the subtree itself, of course, is a binary search tree. any subtree in a binary search tree will also be a binary search tree. So even after deletion, even after the rearrangement, property of the tree that for each node, nodes in left should be lesser and nodes in right should be greater in value is conserved. So this is what we need to do to delete a node with just one child or a node with just one subtree. Connect its parent to its only child and then wipe it off from memory. There are only two nodes in this tree that have only one child. Let's try to delete this other one with value 3. All we need to do here is set 1 as left child of 5. Once again, if there were some more nodes below 1, then also there was no issue. Okay, so now we are good for two cases. We are good for leaf nodes and we are good for nodes with just one child. And now we should think about the third case. What if a node has two children? What should we do in this case? Let's come back to this node with value 15 that we were trying to delete earlier. With two children, we can't do something like connect parent to one of the children. While trying to delete 15, if we will connect 12 to 13, if we will make 13 the right child of 12, then we will include 13 and anything below 13. That is, we will include the left subtree of 15, but we will lose the right subtree of 15. That is 17 and anything below 17. Similarly, if we will make 17 the right child, then we will lose the left subtree of 15. That is 13 and anything below 13. Actually, this case is tricky, and before I talk about a possible solution, I want to insert some more nodes here. I want to have some more nodes in subtrees of 13 and 17. The reason I'm inserting some more nodes here is because I want to discuss a generic case, and that's why I want these two subtrees to have more than one node. Okay, coming back. When I'm trying to delete this node, my intent basically is to remove this value 15 from the tree. My delete function will have signature something like this. It will take pointer or reference to the root node and value to be deleted as argument. So here I'm deleting this particular node because I want to remove 15 from the tree. What I'm going to do now is something with which I can reduce case 3 to either case 1 or case 2. I'll wipe off 15 from this node and I'll fill in some other value in this node. Of course, I can't fill in any random value. What I'll do is I'll look for the minimum in right subtree of this node and I'll fill in that value here. Minimum in right subtree of this node is 17. So I have filled 17 here. We now have two nodes with value 17. But notice that this node has only one child. We can delete this node because we know how to delete a node with one child. And once this node is deleted, my tree will be good. The final arrangement will be a valid arrangement for my BST. But why minimum in right subtree? Why not value in any other leaf node or any other node with one child? Well, we also need to conserve this property that for each node, nodes in left should have lesser value and nodes in right should have greater value. For this node, if I'm bringing in the minimum from its right subtree, then because I'm bringing in something from its right subtree, it will be greater than the previous value. 17 is greater than 15, so all the elements in left of course will be lesser, and because it's the minimum in right subtree, all the elements in right of this guy would either be greater or equal. We'll have a duplicate that will be equal. Once the duplicate is removed, everything else will be fine. In a tree or subtree, if a node has minimum value, it won't have a left child, because if there is a left child, there is something lesser. And this is another property that we are exploiting. Give this some thought. In a tree or subtree, node with minimum value will not have a left child. There may or may not be a right child. If we would have a right child, like here we have a right child, so here we are reducing case 3 to case 2. If there was no child, we would have reduced case 3 to case 1. Okay, so let's get rid of the duplicate. I'll build a link like this, and after deletion, this is what my tree will look like. So this is what we need to do in case 3. We need to find the minimum in right subtree of the targeted node, then copy or fill in this value, and finally we need to delete the duplicate or the node with minimum value from right subtree. There was another possible approach here, and I must talk about it. Instead of going for minimum in right, we could also go for maximum in left subtree. Maximum in left subtree would of course be greater than or equal to all the values in left. Maximum in left subtree of node with value 15 is 14. I'm copying 14 here. Now all the nodes in left are lesser than or equal to 14, and because we are picking something from left subtree, it will still be lesser than the value being deleted. 14 is less than 15, so all the nodes in this right subtree will still be greater. And if we are picking maximum in a tree or subtree, then that node will not have a right child, because if we have something in right, we have something greater, so the value can't be maximum. The node may have a left child. In this case, node with value 14 doesn't have a left child, so we are basically reducing case 3 to case 1. I'll simply get rid of this node. So we are looking good even after deletion. In case 3, we can apply any of these methods, and this is all in logic part. Let's now write code for this logic. I'll write C++ and we will use recursion. If you're not very comfortable applying recursion on trees, then make sure you watch earlier lessons in this series. You can find link to them in description of this video. In my code here, I have defined node as a structure with 3 fields. We have one field to store data, and we have 2 fields that are pointers to node to store addresses of left and right children. And I want to write a function named delete that should take pointer to root node and the data to be deleted as argument, and this function should return pointer to root node because the root may change after deletion. What we are passing to delete function is only a local copy of root's address. If the address is changing, we need to return it back. To delete a given value or data, we first need to find it in the tree, and once we find the node containing that data, we can try to delete it. Remember, the only identity of tree that we pass to functions is address of the root node, and to perform any action on the tree, we need to start at root. So let's first search for the node with this data. First, I'll cover a corner case. If root is null, that is if the tree is empty, we can simply return. I can say return root or return null here. They will mean the same because root is null. Else, if the data that we are looking for is less than the data in root, then it's in the left subtree. The problem can be reduced to deleting the data from left subtree. We need to go and find the data in left subtree. So we can make a recursive call to delete function passing address of the left child and the data to be deleted. Now the root of the left subtree, that is the left child of this current node, may change after deletion, but the good thing is delete function will return address of the modified root of the left subtree, so we can set the return as left child of the current node. Now if data that we are trying to delete is greater than the data in root, we need to go and delete the data from right subtree. And if the data is neither greater nor lesser, that is if it's equal, then we can try deleting the node containing that data. Now let's handle the 3 cases one by one. If there is no child, we can simply delete that node. What I'll do here is I'll first wipe off the node from memory, and this is how I'll do it. What we have in root right now is address of the node to be deleted. I'm using delete operator here, and that's used to deallocate memory of an object in heap. In C, you would use free function. Now root is a dangling pointer because the object in heap is deleted, but root still has its address. So we can set root as null, and now we can return root. Reference of this node in its parent will not be fixed here. Once this recursive call finishes, then somewhere in these 2 statements, in any of these 2 statements, in any of these 2 else ifs, the link will be corrected. I hope this is making sense. Okay, now let's handle other cases. If only the left child is null, then what I want to do is I first want to store the address of current node that I'm trying to delete in a temporary pointer to node, and now I want to move the root, this pointer named root, to the right child. So the right child becomes the root of this subtree, and now we can delete the node that is being pointed to by temp, we will use delete operator. In C we would be using free function, and now we can return root. Similarly, if the right child is null, I'll first store the address of current root in a temporary pointer to node, then I'll make the left child new root of the subtree. So we'll move to the left child, and then I'll delete the previous root whose address I have in temp, and finally I'll return root. Actually, we need to return root in all cases, so I'll remove this return root statement from all these if and else if, and write one return root after everything. Let's talk about the third case now. In case of two children, what we need to do is we need to search for minimum element in right subtree of the node that we are trying to delete. Let's say this function find min will give me address of the node with minimum value in a tree or subtree. So I'm calling this function find min, and I'm collecting the return in a pointer to node named temp. Now I should set the data in current node that I'm trying to delete as this minimum value, and now the problem is getting reduced to deleting this minimum value from the right subtree of current node. With this much code, I think I'm done with delete function. This looks good to me. Let's quickly run this code on an example tree and see if this works or not. I have drawn a binary search tree here. Let's say these values outside these nodes are addresses of the nodes. Now I want to delete number 15 from this tree, so I'll make a call to delete function passing address of the root, which is 200, and 15, the value to be deleted. In delete function, for this particular call, control will come to this line. A recursive call will be made. Execution of this call delete 200, 15 will pause, and it will resume only after this function below. Delete 350, 15 returns. Now for this call below, we will go inside the third else in case 3. Here we will find the node with minimum value in right, which is 17, which is 400. The value is 17. Address is 400. First we will set the data in node at 350 as 17, and now we are making a recursive call to delete 17 from right subtree of 350. We have only one node in right subtree of 350. Here we have case 1. In this call we will simply delete the node at 400 and return null. Remember, root will be returned in all calls in the end. Now delete 350, 15 will resume, and in this resumed call we will set address of right child of node at 350 as null. As you can see, the link in parent is being corrected when the recursion is unfolding and the function call corresponding to the parent is resuming. And now this guy can return. And now in this call we will resume at this line. So right child of node at 200 will be set as 350. It's already 350, but it will be written again. And now this call can also finish. So I hope you got some sense of how this recursion is working. You can find link to all the source code and code to test the delete function in description of this video. This is it for this lesson. Thanks for watching.